This is the video lesson for free body diagrams. The learning target for this lesson is, I am learning to describe the forces exerted on an object or system using a free body diagram. The success criteria for this lesson are, I can draw a free body diagram with the forces acting on an object. I can use a free body diagram to analyze the forces acting on an object. And I can determine the net force acting on an object. So let's talk a little bit about how to draw free body diagrams. So we're going to start with a dot representing the center of mass of the object. Then you're going to draw a box around the dot. So this is an optional step. You're going to see free body diagrams with and without the boxes. I tend to draw the box, but you certainly don't have to do that. Next, you're going to draw arrows from the box representing the forces interacting with the object. So this is the most crucial step. So the longer the arrow, the stronger the force, and the arrows should be in the same direction as the forces. So remember, this is the key thing. Forces are vectors. So drawing the length of the arrow correctly and the direction that the arrow is pointing correctly are key to drawing a correct free body diagram. So you're going to label the arrows with which forces they represent, and then you're going to determine the net forces on the object. Okay, let's look at an example on how to draw free body diagrams. So we have this cabin of a small freight elevator is secured to a motor by a cable and is moving upward while slowing down. There is no contact between the cabin and the elevator shaft. Ignore air resistance. So I'm going to start with our dot. I'm going to draw a box around it. Again, this is not necessary, but I like to do it sometimes. So our first force that we're going to draw is our gravitational force. And then we have an upward force, which is the tension force. So we don't have any force, so there's no contact between the cabin and the elevator shaft. So there's no forces to the left or right. We know that the upward force, so this is going to be a tension force because it's a cable. We know that the tension force is smaller than the gravitational force, which this is Fg. We can say that Fg is equal to m times g. That's the mass of the elevator times the gravitational acceleration, g. And we don't know what the tension force is, so we can leave it as this. But we know that the tension force is smaller than the gravitational force because it is moving upward while slowing down. So the gravitational force has to be larger than the tension force. All right, so that's how you would draw this free body diagram. We don't have any numbers or anything, so we can't do any math with it, but we can do that small bit of analysis in knowing that the gravitational force is greater than the tension force because it is moving upward and slowing down. Okay, in this example, we've got the diagram shows the directions and magnitudes of the forces exerted on a puck on a horizontal surface. What is the magnitude of the vector sum of the forces exerted on the puck? Okay, so we already have a free body diagram drawn for us here. So we've got a force of 2 newtons in the upward direction and a force of 5 newtons in the downward direction. And then we've got a force of 3 newtons in the rightward direction and 7 newtons in the leftward direction. So we're going to figure out what the sum of our forces are in the left and right direction and the up and down direction, and then we're going to figure out what the resultant force is. So what's the vector sum? Okay, so we're going to do a sum of forces in the x direction first. So we have 3 newtons minus 7 newtons. So because our 3 newtons are to the right and our 7 newtons are to the left, the 3 newtons are positive, the 7 newtons are negative. So we have minus 4 newtons on the x direction. Then we have the sum of forces in the y direction. So in the y direction we have 2 newtons upwards and 5 newtons downwards. So we have minus 3 newtons. Okay, so what we're trying to figure out is this resultant vector that is somewhere like this. So what is this vector? And we just want the magnitude. So we don't care about the direction. So the magnitude, remember, of a vector, so we have this vector, which is the vector in the x direction. So we have this x vector and we have this y vector. So we are going to do the vector sum. So the vector sum, remember, is, so we say f is equal to, so f squared is equal to fy squared plus fx squared, because we're talking about the Pythagorean theorem here. So f then is equal to the square root of fy squared plus fx squared. Okay, so f then is equal to the square root of fy is minus 3 newtons squared plus minus 4 newtons squared. So if you recognize this triangle here, so this is 4 newtons, this is 3 newtons, and this would be a 5 newtons. So this is a 3, 4, 5 triangle. So this is a vector. So we're going to put the little arrow on top here. So we have so 3 squared is 9, plus 4 squared is 16. So 9 plus 16 is 25. So the square root of 25 is 5. So we have the force, the magnitude of the force is 5 newtons. We don't care what direction it's pointing in. Okay, we have one more example here. So we are calculating forces using free body diagrams. So a platform of mass m is held at rest by 2 ropes connected to its ends, as shown in the diagram on the left. A block also of mass m. So we have 2 things of mass m. So the platform itself as well as the block are both mass m. It's placed on the center of the platform. The student draws a free body diagram representing the forces exerted on the platform while it is at rest, as shown in the diagram on the right. Which of the following claims best explains why the diagram is incorrect? So our claims are: A, the tension forces from the ropes do not point in the correct directions. The diagram does not include components of the tension forces in the rope. The horizontal forces are unbalanced, or the vertical forces are unbalanced. So what we need to do here is break up our tension forces into the vertical components and the horizontal components and compare them. So these are at 45 degrees, the tension forces. So you can think of this as 45 degrees. So sine of 45 and cosine of 45 are the same number, and it's a little bit less than 7. It's about 70% or 0.7. So our horizontal force is going to be a little bit less than 3/4. So that's tension in the x direction, and we'd also have tension in this x direction. So those 2 tension forces are balanced. But then we have tension in the y direction. So we have 2 components of tension in the y direction. So we have this tension and we have this tension. So that's tension in the y direction, and this is also tension in the y direction. And then we have our normal force and our gravitational force here. So normal force and gravitational force. And you can see that our 2 tension forces plus our gravitational and our normal forces, when we add those forces together, are not equal to each other. So they are definitely unbalanced. So our correct answer then would be D. All right, so what have we learned in this lesson? So we learned how to draw free body diagrams. You start with a dot, which represents the center of mass of the object, and then each force is represented by a force vector. Then you're going to analyze the forces. So based on the free body diagram, determine the object's motion. Lastly, you're going to find the net force. So you're going to add the forces in each direction to determine the net force on the object. All right, thanks everybody.